For this example, we're going to be using this birth weight data set. And this comes from a survey conducted in hospitals. Every time, and by law, a baby is born, a hospital social worker has to ask the parents or the mother questions. And it is like a survey, right? So the variable of interest for in that data set is birth weight, right? What was because the weight at birth is a very good predictor of baby's health. Social workers and doctors are very interested in baby's weight to see potential complications or potential need that family may have, right? So I am looking at the data set right now, and I have the code book here. And so the first variable is family income in $1,000. This is an old survey, 1988. And they have the birth weight in ounces, the father education, the mother's education, what order of the child is this the first, second, third child, etc., whether the gender of the child, whether the baby's race, the number of cigarettes that a mother smoked per day while pregnant, the natural logarithm of birth weight, the birth weight in pounds, the number of packs of cigarettes smoked a day while pregnant, the log of family income, and this dichotomous variable that says low birth weight. And this one is just a categorical variable that looks at whether it classifies the baby, whether the baby was low birth weight or normal and high birth weight. And by the way, a baby is considered being born with low birth weight if the weight is lower than 5 pounds 8 ounces. Okay, so let's go look at the data, and you can see here this baby, right? The first observation is 7 pounds. It's of normal, right? The family income for that is 7,000 a year. Again, this is 1988. For this second baby, it's 5 pounds, right? Square. That's a low birth weight, right? So anyway, this is the data set. Let's say we're going to look at whether family income is related to a baby's weight, right? We want to see if the average income for family income for babies that are born at a normal or high weight is equal to the average income for families that have babies that have been born with low birth weight. Okay, so the way we would do that is we are going to go to data, and we're going to ask for a pivot table here, and in a new sheet. Okay, and the first thing we're going to do is look for the values here and ask for this family income. This is the variable of interest that we want, right? And this is going to give us a sum, but what we want is first an average, and this is the average family income, right? And then we're going to add also, that's the average family income. We're also going to add, again, for family income, we're going to ask for the standard deviation, right? It's 18.7. And we're going to add one more thing, the count for family income, to see how many observations we had. Okay, so this is the entire group, right? We have the average family income is 29. That's in thousands, right? So $29,000. And that's based on 1,388 babies or babies' families. And the standard deviation is about 19. This is for the whole sample, right? Good. Now, let's bring this to the rows, this group that we want to classify this by, right? So we want to know if the average income is different for these babies, right? That are born either with low birth weight or normal and high birth weight. And we put it on the rows. And now we can see here, right? We see that the average family income for those that are born at what low birth weight is 26, right? And those that are born with normal or high is 29, not 29,000, right? So there is a difference there of 3,000, right, in this sample. And the standard deviation is pretty similar in both groups, right? Now, there is 126 babies that were born with low birth weight, and 1,262 babies that were born with normal or high weight. So based on this sample, we could say that in this sample, babies that are born in lower weight tend to have lower income, right, than babies that are normal or higher weight. Their average income, family income, is higher for them. Now, that's in the sample. So we're going to conduct a t-test to see if this is just because of sampling error or not. We're going to rule out that. All right. So the way to do that, we're going to go back to the data, because unfortunately, we're going to have to use all the data here. And for that, I'm going to make a little table of results here, right? So I'm going to do two tests, one for unequal variances, here, one for equal. And then, let me move this a little bit. And here we're going to have the first we're going to calculate the degrees of freedom, right? Then the critical value, then the p-value for the t-test, and also the t-statistic for the test, right? We're going to calculate all that. So remember that the first step, in conducting a t-test is to determine which test to use, right? And for that, we need to ask ourselves first, are the two samples matched, right? Are they dependent on each other? So you have a baby that was born with a low birth weight, right? That's one sample. And babies that were born with normal or higher weight. Are they dependent on each other? Are we observing one group because we observe the other? No, right? They're independent. These are independent observations. The fact that we're observing one doesn't depend on the fact that we're observing the other one. So they're not matched, right? So we're not using a type 1 test, right? Just like most surveys are. So we are using, they're not matched, right? Now we have to ask ourselves, are the variances in the population different or similar? Now, when we looked at the standard deviations for them, they were kind of similar, right? But these are sample standard deviations, right? So I guess we could, I think a type 3 test would be the best one here. But we're going to conduct both, assuming equal variances and assuming equal variances, because it's just a click on Excel, right? All right, so we determine it's not matched, and we're going to do these two t-tests. The next step is to state the null hypothesis and the alternative hypothesis, right? So we can do that here. So HO is, there is no difference in family income in the population between the two groups, right? The low birth weight and the normal birth weight, there's no difference in family income. That's HO. And the alternative would be, there is a difference in the population between family income across both groups. There is a difference. All right, good. The next step, right? We're not going to deal with directional hypothesis. We're just going to do two tails. Is to determine what significance level we're going to use, right? And this significance level is the probability of incorrectly rejecting the null hypothesis. We want to keep it small. By convention, the most you can go is 5%. Other people would not look at results that are not at least at the 1%, right? You can use 0.5, 0.05, or 0.01. We're just going to use 0.05 for now. The next, the next step is to calculate the degrees of freedom, right, for our test. We're not using a type 1, we're using a type 2 or type 3, right? So for equal variances, the degrees of freedom is given by N1 plus N2 minus 2, right, for equal variances. How many observations do we have? We have N1, this is one group, we have 126, plus N2, right? That's 1262. If you add them, we have 1,388. And the formula says it's one group plus the other, 1,388 minus 2. So that will give us 1,386. So we go back here to our data. And here for equal variances, our degrees of freedom is 1,386. And for unequal variances, what is the formula? Is you get the smaller group and you get the n minus 1, the n minus 1, or n2 for the minus 1, and you pick the smaller one. So if we go see our data set, the n for this is 126 minus 1, 125. The n for this is 1262 minus 1, 1261. Which one is smaller? This one, right? The 125. So here, 125. All right. We have determined our alpha. We have determined our degrees of freedom, right? Now we need to determine what's our critical value, right? And remember, we would do this with a table, right? We could do this with a table. If you get you know, the probability on the top of the table and the degrees of freedom, and then look at that number, and that will be our critical value. But we can use this little formula here in Excel to tell us that without having to go to a table, right? And it's T inverse, where you put your alpha here, this probability, comma, and the degrees of freedom. It's as simple as that. So we're going to do that. So equal T inverse. And again, it's going to ask us the probability that we chose. So we're going to use 0.05, comma, and the degrees of freedom. And the degrees of freedom in this case are this, right? The whole sample size minus 2. So 1,386. Close parentheses and enter. And our critical value is 1.9616. Right? This is a pretty large sample, so it is pretty much the same as a normal distribution. All right, now let's look for this other one, right? It's the same formula, but now our degrees of freedom are a little different. So equal T inverse, open parentheses, our alpha is 0.05, and then comma, and then degrees of freedom is 125. Close that, and we have our T value, our critical value is a little bigger, right? So assuming unequal variances is a little more conservative than assuming equal variances. But anyway, there you go. So the next step is to get the T statistic for your test. But in Excel, we can't do that directly. We need the p-value first. Okay? And just like in the chi-square test, remember that function chi-test would give us the p-value for the test. Here, the function that we're going to use is t-test, and that's going to give us the p-value for our test. Okay, and this function t-test is asking you for 4 things this time, right? It's asking you first for, give me all the values for the first group. That would be all, give me the family income for all the babies with low birth weight. Then comma, then give me all the values for the family income for all the babies with normal or higher birth weights, right? These are 2 arrays. Comma, then is going to ask us, what type of test are you using? 1 tail or 2 tails? And we're using 2 tails. So we're going to put a 2 here. And then is going to ask us, what type of t-test are you using? A 1 per samples, 2 non-paired equal variances, or 3 non-paired unequal variances. All right, so this is pretty straightforward. The only little complication here is that we have to select all the values for each group. So let's go and do that. Now we have to select all the family income for families that had babies of low birth weight, and families that, and then select all the incomes for families that have the normal and high weights. So that means that we're going to have to sort this data set, right, by this variable. So the way to do that is we select the data set, okay, and then we're going to go to data, and we're going to click this sort range. We click on that, and this is very important. Your data has the variable names on top. On the first row, it has variable names, right? So you have to click that And now it's going to know that the first row is the variable names. And then it's going to ask you, this immediately changed. See, that immediately changed. And it's going to ask you, how do you want to sort? Which variable you want to sort them by? And we're going to sort by this because this is our grouping variable, the low birth weight. That's the variable we're using to group. And then we're going to A through C or C to A, doesn't really matter because there's only two groups. And then if we press sort, you see immediately the whole data has been rearranged and sorted by this variable, right? So we're seeing this, all the data for babies that had low birth weight, right? And then below them, we're going to see babies that had normal or high weight. This is their data. Okay, so good. We have our data sorted now by these grouping variables. So now we can calculate the p-value. So we're going to do that by saying equal t-test, and then open parentheses. Now we have to select the variable for the first group, right? The values of the variable for the first group. So this is family income for this first group of low birth weight. So we're going to start selecting them and going down. Remember, there's like 126 of them, right? So when we get to 126, we should be getting close now. And boom. So up to 127, that's the first group, right? This is the family income for babies that had low weight. Then we hit comma. And now we have to select the family incomes for babies that had normal or higher birth weight. So we go here and select them all, and it's 1,388. So have a ways to go. This is the only kind of tedious thing about the test. Otherwise, it's just a formula. There you go. So we got them. Now, comma. So the next thing we need to tell Excel is what type of test? Is it one tail or two tailed? And we said we're always going to do two tails, comma. And then it's going to tell us what type of t-test are you conducting? Is it a paired samples or matched samples? No, it's not. Are you assuming unequal variances or equal variances? Well, we're going to do both. We're going to do equal variances, and that's a 2. So 2, and that's all we need. We close parentheses, and we hit OK. And we get a p-value there, right? This is assuming equal variances. Good. Now we're going to do the same t-test, but now assuming unequal variances. All right, so we use the same. Equal t-test. And now we have to select, again, the incomes, family income for those who have low birth weight, for babies who have low birth weight. And it's 126 of them. There. And then comma. And then we select the incomes for babies who have normal or higher weight. There. And then comma. And then you want how many tails? 1 or 2 tails in your test. And we're going to say 2 always. And then what type of test are you using? Matched or non-matched? Non-matched. Okay. Equal variances? No, we already did that one. Now we want unequal variances. So we put a 3. And enter. All right. Wow, this ended up being a fascinating example. Good, excellent. So now we have our p-value. We could stop here, right? But we're going to go over the next step. We're going to actually calculate the t-statistic for the test. And for this, we're going to use again oh, sorry. We're going to get the t-statistic for our test, and we're going to put the p-value here. Again, this function, t inverse, the p-value and the degrees of freedom. So equal to t inverse, and we're going to put this p-value there, and the degrees of freedom is 1,386. And same for here, equals to t inverse. We're going to put this p-value there, and comma, and the degrees of freedom 125. Okay, now we have everything we need to do this. Now, what do we conclude? Okay, well, let's start with the p-value. Let's look at this equal variance here. And let's look at the p-value here. If our p-value is lower than our alpha, right? That's what we said. And let's put the alpha here so that we remember. If our p-value is lower than our alpha, then we would reject, right? So assuming equal variances, our p-value is, wow, it's almost 0.5, right? I mean, if we round this, it is actually 0.5. If we would round it, it would be 0.5. But it's a little smaller than 0.5. So in theory, we could reject this, right? There is, we would have, because our t-statistic that we got for our test is 1.97, right? And there's less than 5% chance that we would get a 1.97 if the null was true, right? Remember, this t-statistic, it's a little bigger than the critical value, right? I mean, at the third decimal, it is a little bigger. So in theory, we would be able to reject, right? If we were assuming that the variances in the population are equal, then we can reject the null and say that there is a difference between the population and family income, between family income, the family incomes for babies that are born at a low birth weight and those that are at a high birth weight. It's very close. Now, if we assume unequal variances, our p-value is actually higher than alpha, and our critical, our t-statistic is smaller than the critical value. So if we assume unequal variances, then we cannot reject the null. Then we would say that we don't have enough evidence to say that the family incomes for families who have low birth weight are different than those who have high birth weight, right? So that is how you would conduct a t-test, right? So the first thing you would do, remember here, we calculated the average. There was a $3,000 difference in the averages. And we did the hypothesis test, assuming equal variances and assuming equal variances. And it comes really close when we assume equal variances. We barely reject the null at the 5% level. And in assuming unequal variances, we cannot reject the null, right? So sometimes it makes a difference. When the difference is really, really small, assuming equal variances or assuming non-equal variances can make a difference. Now, in this case, you can say, you can reject assuming equal variances, but it's so close that you may get some pushback there. It's really pushing it. Anyway, that's how you would conduct a t-test using Google Sheets.